Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program at the University of Ontario Institute of Technology, also known as Ontario Tech University. So I also took my Bachelor's of Science there in pharmaceutical chemistry as well. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now I'm just going to go and get started on our set of questions for today. Okay, so the first question asks to select the reagents, then draw the neutral organic product of the Wolff-Kishner reduction. Okay, so question number 1. And they want us to draw the neutral organic product of the Wolff-Kishner reaction. So for the Wolff-Kishner reduction, the reagents that you would use for this, N2H4, and the potassium hydroxide. And basically what this reduction reaction is that it reduces your carboxyls, such as your aldehydes or ketones, but it doesn't just reduce it to an alcohol. It reduces it completely to a methylene group. So methylene, it just means like CH2. So there's no oxygen whatsoever after the Wolff-Kishner reduction. Okay, so let me write out the reagent that they gave us. So we have this benzene ring, then attached to it like our ketone, and then the reagent I'm going to use is N2H4 and potassium hydroxide. Okay, so I'm just also going to write down the mechanism for this reaction as well. Okay, so first, the benzene ring kind of looks like this. And then our ketone is replaced with these two nitrogen groups. Kind of like that. And then from here, an OH minus comes in and deprotonates, bringing this down. And then we're just left with a negatively charged nitrogen. Okay, so after this, the negative charge comes down to form a new double bond there. And then this double bond gets reduced. And then the product after that has the new nitrogen double bond and a proton there. And then from there, another OH minus comes in, deprotonates hydrogen, and now we have a negatively charged nitrogen group. Then lastly, this negative charge goes in like that, breaking this carbon-nitrogen bond and taking one of the hydrogens with it. Then our final product looks like this. And then I'll also show the two new hydrogens that are now there instead of the ketone. Okay, so that's our final product. Let me just put it in a box. And let's look at the answer that our junior tutor said. Yep, so that is correct. And we can go on to question number 2. So question number 2, draw the products of the complete hydrolysis of a ketal. Draw all products of the reaction. Okay, so let's draw out this whole thing. I'm just drawing it out, like showing all the carbons and hydrogens just to kind of make it look more clear. Okay, and then this is plus water. I'm gonna go down. so that there's more room. So basically when you have a Ketal reaction, I'm gonna draw out like the bonds that are breaking, and everywhere that there was an ether group is now going to become an alcohol. So let me just pretend like this bond broke first, and then I'll write out the first products that you would get if this bond were to break. So we have a new alcohol that was formed there. This is just going to be product 1. And then this ether stays the same. And then on the other side, we're going to have a new alcohol right here. So I'll call this products 1 and 2. And then let me also draw out what would happen if this bond were to break instead of the blue one. You would get the following products. Okay, so you can see there's a new alcohol group here now. And I'll just call this product number 3. And then product number 4, just the other half. And then that's product number 4. But it doesn't end here, because products 1 and 3 actually can undergo just another reaction. So I'm gonna draw it out. Yeah, maybe I'll draw it out on the next page. So I'm just gonna draw out product number 1 again. This is question 2, continue. Product 1 looked like this. So this can undergo another hydrolysis reaction. So I'm just going to show the plus water. And then an H plus. And then you get the following products. So you can see that that alcohol is now a ketone. And then the other byproduct is just another OH. So I'll call this product 5. And then if we go to our previous page, you'll see that the second byproduct is the same thing as product number 4. So this isn't a new compound. I'm just going to name it product number 4 again. And then let me just do the same thing with product number 3. And remember, look like this. With the alcohol here. It's product 3 plus water, an H plus up here. And now you have a new product formed. So this time ketone is formed. So you'll notice it's the same thing as compound number 5. And then the other alcohol that is formed as a byproduct is here. Then if we look at the previous page, that this is the same thing as product number 2. Okay, so it might look a little confusing at first, but basically these are all of the products that you could possibly obtain from the complete hydrolysis of a ketal. So we have this 1, 2, 3, 3, 4, and 5. Let's see the answer from our junior tutor. They have this one here, and then they have the final versions of 2 and then 4. So this product is correct. All right. So we can move on to question number 3. Draw the correct products for the following reaction. Question number 3. Okay, and our reagents are chlorine, and sodium hydroxide in the first step. Then H3O plus, which is probably used as the workup step. Okay. So when you have these reagents like the chlorine with reacting with a ketone group, first the ketone will react. Then a hydrolysis reaction takes place to form a carboxylic acid group. And chloroform. Okay, so our final product will look like this. We have a new carboxylic acid. And chloroform is a product as well. Okay, so let's look at the answer from our junior tutor. They got the same thing. So this solution is correct. And we can move on to question number 4. It's a lot of organic today. Draw the major organic product in the reaction below by adding to the pre-drawn structure. So let's see. And you notice that they specified that there is only one equivalent of bromine Br2. And then FeBr3. Okay, so this is an example of Friedel-Crafts. And basically what this question is asking is what part of the benzene will it brominate. And by brominate, I mean like where in the ring will you add a bromine group. So if we look at the substituents of the ring, you'll see that there is an oxygen group here. And oxygen is an example of an electron donating group. So therefore, it will direct your electrophile to the para position. Okay, so let me write out what the final product would look like. You have your benzene. You just draw out everything first. And then the para position is here. So this is where our bromine group is going to go. And this will be our major product. Okay, so let's look at the answer from our junior tutor. Explanation. Oxygen is an electron donating group which directs the incoming electrophile to pair up position. Okay, so solution is correct. So we can move on to question number 5. Draw a stepwise mechanism for the following reaction. So this person needs help with part 2. Looks like they already wrote out that part. Just so that we're all on the same page, I'll just start from the beginning. It'll probably just be easier to explain from. Okay, so first, this bromine group just leaves. So I think that part was probably given. But basically after the bromine leaves, we have this now positively charged carbon plus a Br minus. So this is where the ethanol comes in. Then basically what happens, that one of the lone pairs on the oxygen will come to try and neutralize that positive charge. And then this affords a new structure that looks like this. Now this oxygen is positively charged. Basically, same thing will happen again to try and relieve that positive charge. So another ethanol comes in. It'll deprotonate that. To neutralize your oxygen. And then we have a product that looks like that. So it is an ether group, and it is the same final product that was given in the question, so we know that we did it right. Now let's see the answer from our junior tutor. Yep, starting from part 2, they have the ethanol come in. Yeah, same thing where they just have the bond here, trying the electrons from this bond, trying to just neutralize that. But it's always good practice to show how that happened, and that's why I just kind of drew out ethanol group coming to deprotonate it. And then we're left with that as the final product. Okay, so we can now move on to question number 6. Give the expected major products of the following electrophilic aromatic substitution reaction. Okay, so let's write out what we're given. So this is using aluminum trichloride. And this is kind of similar to that other question where we want to try and figure out whether where on the benzene ring will the new substituent go. So let's look at what is on the benzene ring. We have a nitrogen group that has 2 methyls on it. Okay, so this is an example of an electron donating group. So in this case, it'll form either the para or the ortho product. So let me write out what this would look like. Okay, so the one on the blue is an example of the para product. Then I'll do an ortho product in red. Okay, so this is the ortho product. Let's check out the answer from our junior tutor. They got the same products, and they said the Friedel-Crafts acylation of substituted benzene produces para product as the major product. And then this nitrogen with 2 methyl groups is an electron releasing group which donates electrons to the benzene ring and forms ortho or para product. Okay, so this answer is correct. And then we can move on to question number 7. What is the formal charge on phosphorus in a Lewis structure for the phosphate ion that satisfies the octet rule? Okay, so I'm gonna draw out 2 different two different forms of the phosphate ion. So phosphate is PO4 3 minus, and basically it can be written like this. Where one of the oxygens has a double bond. And then it can also be drawn like this. Where all of the oxygens are singly bonded to the phosphorus. So just out of curiosity, let's calculate the formal charge. I'll call it product of phosphorus ion A, phosphorus ion B. So let's calculate the formal charge of the phosphate ion A. So the equation for formal charge is equal to the number of valence electron minus the number of bonds. So another way people write out this equation is that they just say the number of bonding electrons divided by 2. Or similarly, you can just say the number of bonds. It gives you the same number in the end anyways. And then also subtracted is minus any lone pairs, and this is on phosphorus. So the valence electrons on phosphorus is 5. The number of bonds are 1, 2, 3, 4, 5 for the ion A. And there are also no lone pairs. So the formal charge is equal to 0. And then let's do the same thing for phosphate ion B. Again, the number of valence electrons is the same for phosphorus. It's just 5. The number of bonds, however, changes. Instead of 5 bonds, there are now 4. But again, there are no lone pairs on phosphorus. So this time, there is a +1 charge for phosphorus. So the question is asking, what is the formal charge on phosphorus in a Lewis structure for the phosphate ion that satisfies the octet rule? So if you look at both A and B, B is the one that satisfies the octet rule. So that just shows that it has the 8 electrons in its shell. Right, let me rewrite this so that you can see it. Yeah. So this satisfies the octet rule. So the formal charge would be the +1 as our answer. So let's look at the answer that our junior tutor said. PO4 3- ion Lewis dot structure can be expressed in two ways. In the first way, the phosphorus atom is doubly bonded to one of the oxygen atoms and singly bonded to the other 3 atoms. This Lewis dot structure clearly does not comply with the octet rule, as it will have 10 electrons in the valence shell of phosphorus. The formal charge on phosphorus would be 0 for this structure. Formal charge on doubly bonded oxygen would be 0, and the 3 singly bonded oxygens would be -1. The other structure would be a single bond of phosphorus to all 4 oxygen atoms. The structure would satisfy the octet. For this case, the formal charge on phosphorus would be +1, and all the 4 oxygen atoms would be -1. So the answer would be +1. That was very well written, so this solution is correct. Okay, so now I think we have room for one more question. Question number 8. How do decantation and filtration differ? Which should be faster? Okay, so let me make a little table. So I'm no artist, but I'm just gonna try draw out what decantation looks like. So basically for decantation, your solution is either slowly poured out or you can just transfer it out using a pipette or something. But basically, you have to wait until your particles are settled at the bottom. So in this case, it's red. So I'm going to write that down as well. Need to wait for particles to settle before you start pouring it out. So it seems pretty easy. However, this method is, say, less accurate. I'll call it not too accurate of a method. Okay, so let's compare this with filtration. Let me try to draw it out again. Okay, so you can see with the filter that you don't need to wait for any of the particles to settle or anything. And what filtration does is that it allows definite sized particles to pass through. And then the rest is collected in the filter. So filtration is more accurate. So it doesn't rely on the human error where we would just try to slowly pour out solution and just hope that none of the other particles will go in to our collection vessel. So it's more accurate because like the filter paper that you use, like hopefully it's the right kind of filter paper. It'll just not allow any of the particles that we don't want to go through. So it's more accurate in that sense. But if we want to talk about saving time, I would say that gravity filtration is much more slower than decanting. So it also like depends on how good your filter paper is. So you could have a filter paper that has really small pores, and sometimes it would take like forever for the solution to even pass through it. But if you had a filter paper with like larger pores, um, it wouldn't take so long. So still gravity filtration is much more slower than decanting. But if we use like vacuum filtration, I would say that would speed up the process by a whole lot. So all in all, decantation would be faster compared to like gravity filtration. However, the method isn't as accurate. But if you were to apply a vacuum to your filter, this would definitely speed up the process. So let's just see what our junior tutor said. Decanting, pouring out a liquid off a vessel. Example, a jar filled with water contains settled solubility/sediment. separate the mixture by decantation. The liquid is gently poured out of the vessel into another one without disturbing the sediment. Filtration. This is where the filter paper is used. This is the arrangement. A retort stand attached to it is a filter funnel that contains the filter paper. Below the funnel is an empty beaker. The mixture to be filtered is poured into the funnel, passing through the filter paper. The mixture is now separated with the liquid part, called the filtrate, in the beaker, and the impurity, called residue, is trapped in the filter paper. Both separation techniques are used to separate solid-liquid mixtures, with the solid being insoluble. The former is used when the solid is sort of heavy and can easily settle at the bottom, while the latter is used when the solid is fine and dispersed throughout the liquid. Decantation should be faster. This is a long answer. Let me just read through it. They go into detail about if more water is used, decantation will definitely take less time than filtering. Yeah, it also depends on how much water you actually have. If the two substances are thoroughly immiscible, just allow it to stand and pour out the liquid carefully. If, on the other hand, the two mix somewhat, it is better to pass the mixture through a fine sieve, which allows out the liquid but retains the solid. This is filtration. The question is, which is not fast, but which separates the mixture neatly? Here, filtration undoubtedly scores. On the other hand, if you're in a hurry, decantation is better. Decantation is a process for the separation. Yeah, so they just talk about decantation and filtration again. Yep. Yep, I think they just have every definition possible on decantation and filtration. So I would say this solution is more than what was needed, but it is still correct and it is still very informative. So I'm just going to say that this solution is correct. Okay, so I think that is all we have time for today. I froze. Okay. Okay, so those are all the questions for today. So if you enjoyed today's Q&A session and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you had any questions of your own that you would like to submit, then check out the links in the description as well. Also, if you liked today's video, please just give it a thumbs up and also leave a comment. And just don't forget to share it with all your friends and classmates if they needed any help with organic or just chemistry in general. So this has been Donna from OneClass, and I hope to see you soon. Bye.